Hello, and welcome back to the Generative AI class. Today, we are going to cover variational autoencoders. So, in last video, we covered autoencoders, and we seen that an autoencoder architecture has three main parts. We have the encoder, the latent representation Z, and the decoder. So, it takes an input, like for example here, the original image representing number 2, passes it through the encoder to produce a compressed representation, and then sends that to the decoder to rebuild the image. During the training, the network minimizes the reconstruction loss, which measures how close the reconstructed image is to the original. The loss is like the square difference between x and x hat. I mean the square difference between the original image and the reconstructed input. So the closer is x hat to x, the smaller the loss, okay? Now, let's simplify this diagram for the upcoming slides. So don't worry when you see something like this. What we'll do is mainly that we are going to hide the internal layers of the encoder and decoder. And we're going only to keep the essential structure of the autoencoder. It's just like simplification or an abstraction, okay? All right. So the basic idea of autoencoders, and if you remember in the last lecture, we were very concerned about Z, about the latent representation. In particular, about the size of Z, okay? So for now, let's ignore the decoder for a moment and let's focus on the first part of the architecture, okay? So the encoder takes the image as input and maps that into a much lower dimensional representation, okay? Z. Think about the dimensions of the input image. Now, that number 2, original image. So, the computer last time, we seen how computers see images. So, how it sees number 2? Mainly, the computer sees that as a matrix, and that matrix actually stores every single pixel as a value. So mainly we can have even millions of or billions, sorry, of values, and once it goes through the encoder, so the latent representation there, that vector Z, is smaller. It has a smaller size, okay? So let's say it's a short vector of numbers, right? And in practice, the dimensions of this video could be 100, 50, or even smaller, like 5 or 4. So no worries. We've seen in lab 1, it was very small, okay? Let's now zoom on these representations. They actually live in a smaller and let me say more interpretable space. This space is known as the latent space. And in a standard autoencoder, the latent representation Z is simply represented with a single point within that space, okay? So once an autoencoder is trained to reconstruct images from latent codes, it seems now reasonable to try generating new images. And when I say generating images, it's mainly given the decoder part, okay? How it works? Mainly by picking an image, we do we have an image. What we will do is we are going to pick randomly a point in the latent space, okay? And by passing that point now, for example, we can randomly get Z1 as a point. And this point, if we are going to pass it through the decoder, we are going to build, or we are going to get the new version or the reconstructed input from that random like point that we got. So in this case, it's weird. If you focus on the representation of this, like just let me, okay, that number 2, it doesn't look actually like number 2. You're going to understand more with other examples. Now, it's the same. If we randomly pick up now another example, let's say Z2, okay? That is absolutely, it has a different latent representation. So the vector is not the same. We don't have the same values. And this is, again, if it's going through the decoder, is going to result in worst reconstruction, like reconstructed version that don't even look like the input. So these reconstructed version now, whether for Z1 or Z2, they are not even looking at like number 2, which is in the original image. Still, we can try more. With Z3 here, we are having like a different latent representation. We have a different vector, and again, we obtain even like a worse reconstruction. Now, the same, no matter how many like points we are going to take in this latent space, if we are going to make them or pass them through the decoder, we are again like getting some reconstructed input, but it doesn't look like the original input. This is the whole idea. So the idea, which is of randomly sampling points from the latent space and decoding them like to generate new images, usually it fails. Now, if we randomly do this and we are trying to generate things, we are going to get things, but not actually that things that make sense, okay? And the first main reason now for all this is that autoencoders, they learn deterministic encoding, which means that each input maps to a single or to only one fixed vector z, okay? So now let's see. With variational autoencoders, now things work a bit differently. So instead of mapping the input into a single point, like or that vector z in the latent space, which is a point at the end, the encoder converts each input into probability distribution. Specifically, we can say that it's a Gaussian distribution. Let me pause here. So, because it's very important, this twist. So, moving from deterministic like setting to stochastic or introducing stochasticity within VAEs is very important. So, we do not longer say like this image is going to become this exact vector. No. So instead, the encoder learns to, let me say, if I have like two quantities, they are going to define my vector in the case of variational autoencoders. Let me explain more. These two quantities, I mean, here you can see mu and sigma, okay? So here we don't only have the like z after encoding, there is not only the latent like representation or the compressed version of the image, there is new like quantities. They are the mean, mu, and the variance, sigma, okay? So for mu, it tells us like where the distribution is centered, okay? And for sigma, it tells us, let's say, how spread out it is, okay? Here, don't worry. I will explain things from scratch. So I am going to open a small parenthesis here. I'm going to take you back, I would say, to the previous lecture and probably to some background before that in probability and Bayesian like thinking, I would say. So when we learn about generating new samples and generating methods, we did this already in the previous class. So what we seen last time, we seen like details in the probability density function, okay? The probability function, density function, like the one on the right that we seen, it looks exactly like the bell. It's kind of continuous function, and this is like mainly how it looks, okay? I would say it's a Gaussian distribution, okay? And it gives us kind of a smooth, continuous region around the central point. This means that we can randomly sample from this distribution and still get meaningful latent representation. And let's say, when I say meaning latent representation, it's like it belongs to the same family of the original input. Like if I'm generating from the input number 2, I am going to have things that are similar, let's say, or around that representation. So today we are going to focus on the concept of sampling, and we will work with discrete distribution. So here, why we move from discrete, I would say, from continuous to the discrete. First of all, when we work on with the like computer or with images, it's not continuous. So we use the idea of sampling, and this is why it's very important to study the probability density function in this case, okay? And so this, like the idea now, when we say that we are going to work with random variables, the idea is that we can assume that the data that we have, okay, or the variables that we have, they are kind of separated variables, okay, separated values, okay? So let's have a random variable x, and in our case, we have x is going to take any value between 0 and 1, okay? So here is what we call the probability density function of x. It looks like this. It basically tells us the probability of a sample being any of the values between 0 and 1. So whenever an event occurs according to the probability distribution of x, we refer to this as sampling from x, okay? And we mainly represent it like this, okay? And the idea here is that the concept of sampling, mainly, it's extremely important for this course. And let me simplify it more with an example. Even that from the start, we were taking Z1, Z2, Z3, and that were examples of sampling. Now let's see it like concretely, okay? So the idea of sampling is exactly like I'm closing my eyes and I am randomly selecting like a point on the x-axis, okay? So it's exactly like I am somewhere here standing, I'm closing my eyes, I'm jumping at some point, okay? So let's just take an example. Let's see, for example, here, the number 4, okay? And this is the point that I am sampling, I say. Means I am randomly choosing. It could be x4, and in this case, I can read, okay? Or I know exactly the probability value for x4. I can simply read it from here, and I will have some exact value, okay? Then now, if I can go and choose another, like, different random variable, let's say I can choose x5, okay? And for x5, again, I have here some probability value corresponding to x5, okay? However, now, if we zoom in between x4 and x5, I have no idea. I don't know, okay? So here it's kind of a continuous information about the probability we have. Here we have a discrete information, means sometimes we don't know in between what we have, okay? It's not like smooth, like on the right, okay, in the continuous one. Here in the discrete case, it's kind of like the stairs. You see, like here is sometimes ups and down because they are discrete like values, okay? It moves like like the stairs, I would say, okay? So now the idea is clear, I guess. And we, like, usually, if we are going to focus on the probability density function, and let's say we usually note P of x, the density of x, which is an interesting quantity, okay, that describes the distribution of x. We can think of the famous expectation. You see the already formula here. I forgot to mention the like animation for this one, but expectation is a very interesting and very important like formula that we can use like if we are sampling from x. But what is that? So it's mainly the average. It's the average value that you can expect when sampling from x, okay? And it can be computed using the integral, like you see in this formula. And this integral of what is the integral of the probability density function. So it can be computed like in this function, okay? Fine. So now let's consider two random variables. Now, when I say random variable, it's clear for everyone, okay? And we will consider in this case x and z, okay? This now 3D shape you can see is the joint probability distribution of both x and z, okay? So you are now looking at the joint probability distribution of x and z. In simple terms, it tells us like how likely each pair of values, I mean, one from x and one from z, is, I would say, likely to happen at the same time, okay? Now, as before, we donate the marginal distribution of x as p of x and the marginal distribution of z as p of z. Note that these are two completely separate densities, like you see in the graph. One, it has one like representation, the other one is having a completely different like representation, okay? And now, although we write both densities with the letter P, so here just to make things clear, okay, I consider that everyone is having no background in my classes. This is why I probably go that much like in detail just to make things simple for everyone, okay? So when you see P, it means a probability, okay? There is no relationship between like P of X and P of Z. And also now, an interesting, I would say, property that you maybe know this, of the joint distribution is that we can use it in order to compute what we call the marginal distribution, okay? And this process is known as marginalization, okay? So mainly this involves the integrating the joint distribution with respect to each or like with respect to the other like variable, okay? So here we have like with respect to z, okay? To find the probability of sampling a specific value according to z, we integrate the joint distribution over all possible like values of z. And in case like similarly, we want to determine the probability of sampling a value according to z, we integrate over all the values like of x. Now, the final concept now I want to cover is the conditional probability, okay? You also might know this, but I'm trying to make things simple, okay? So the term P of here, we have this, we can read this as, sorry, that's the wrong pointer. So we read this as a probability, the conditional probability, the probability of x given z, okay? And this represents the likelihood of the data x, okay, given the latent variable z. This is why here we have given z and always we have like dividing by z, okay? So as you can see, it's expressed using the joint distribution and the marginal distribution, right? Essentially, now I would say it's like taking a slice of the joint distribution and normalizing it by the probability of sampling that value of z. Let's take an example. For instance, like if we want to compute now p of x given z, which is, we consider that z is equal to 23. And what we will do, we simply took all the slice and normalize its value by the probability that z equals to 23, okay? And the same now, if we will consider now p given x, okay? So the p given x now, the probability of, sorry, p of z given x, so the probability of z given x, so we have what we have in here. So you see, where is my cursor? Oops. So x given z, so the given one is x, and this is why we are going to divide by x here. Always learn it like that, as simple as this. So now, if we want to think of it, so this represents the probability that the latent variable z was present when we sampled the data x. We computed just like we did for the other conditional distribution. We are going to consider like this slice, and we are going to normalize it by the probability that that x, sorry, is equal to 9. So now we have got the basics down, and let's say that we are ready to explore the theory behind variational autoencoders. Okay, these were simple things. I'm just covering them to make everyone, let's say, at the same level. Okay, and now, if we want effectively to understand what the encoder and decoder are doing, let's say that they are trying to learn probability distribution for variational within variational autoencoders. Okay, this is why I'm talking on probability distribution mainly. Okay, so the encoder is mainly computing a probability distribution of the latent space given the input data x, and the decoder is doing the reverse. So it's like kind of trying to compute the probability distribution of the data given the latent variable z in this case, okay? So this small modification or twist, I mean, like, instead of like only before we were just having z here. I don't know why it's plotting like this, but it is z, the latent representation. So instead of only considering z as a point deterministic, we are considering mu and sigma in this case, okay? And z in this case, what we are like doing, we are switching, or we are moving from deterministic point in like to the Gaussian distribution. So okay, here z, we are considering it as a Gaussian distribution, and you know that the Gaussian distribution is known with its like mean and variance, mu and sigma. Okay, so mainly this is the mathematical trick that makes variational autoencoders like generative. Okay, so it organizes the latent space, makes it continuous. It allows interpolation and sampling to produce realistic outputs. Let's break this down, okay? Or let's just focus on this little example. Now, what we have in an autoencoder, like the typical autoencoder, before moving to variational autoencoders. Now we are focusing on the autoencoder, where we mentioned already there is a problem that the latent space is unstructured with scattered or irregular representation. So we, in this case, we all agree that Z here is purely deterministic layer, right? So what I mean by purely deterministic layer, that this is like the main reason that the latent space is like not organized, it's like scattered, it's uneven, so is because of this like deterministic nature of the latent space. So the latent space is also, I would say, unlimited. So during the training, what will happen? The model learns all encoder and decoder parameters. It needs like to reconstruct the image based on that. But what happens during the test, we only are going to focus on the decoder side. So we only, during testing, use the decoder because it is the part that generates new images, okay? Now the problem when it comes to autoencoders, it is that the decoder needs a latent vector as input. And what we are giving in this case is this kind of vector, which is like just, let's say, a deterministic, which is represented with a point, okay? So we don't know exactly what is a meaningful vector, okay? Or what kind of vector should like be given to the decoder so that it generates the right representation, right? So here what we have, we can think of like having different example, random, I would say, like points, okay? And what will happen? So there is a large portion of this space, as you can see here. It is like doesn't correspond to real data. Let me take the example of X or Z5 in this case. Now, Z5, what we for Z1, Z2, Z3, and Z4. Now, I'm making them in the same color to show you, like we seen in the start, that these are not clear reconstructed versions of the input. If by any chance I am closing my eyes, I am selecting one point and I'm falling on the Z5 point, okay, in the latent space. I try to plot that or visualize that. What I can have in this case, so I can have it, I would say, garbage. I have some unexplained representation, something that I cannot explain, okay? And so the idea here, the output is not clear, okay? And if I will select Z5, it could be anywhere, okay? And having this kind of output is, I would say, expected, okay? Because the space is, or what we have is the deterministic conditions to the output, okay? So in this case, it will be always garbage. And if we are going to randomly sample, so often it's going, and we are going to decode that random sampling. So it's going to end up with meaningless result, I would say. So from here came our need for a way to determine how this hidden vector exactly must look like, how Z should be, or the latent like space, okay? So here comes the importance of two main properties, okay? What about encoding Z as a distribution? Let's think of it, okay? So instead of having these points, okay, we have them represented as deterministic data points. We will have a distribution, okay, a Gaussian distribution. For each of these z's, we have mu and sigma, and we have a Gaussian distribution, okay? So as you can see here, what we can see, still there is a problem. Still, if you see, the latent space is still fragmented. We still have these different four parts kind of isolated. So we have isolated clusters with empty regions in between them, okay? Still, if we randomly now sample and we take any points from here, like Z5 again, so we can again end up with a garbage reconstruction. So in this situation, the latent space does not guarantee continuity, and also it does not guarantee completeness. And these two are extremely essential properties that variational autoencoders explore or enforce, okay? So, and they do that explicitly, and we will see how. So what actually guarantees both completeness and continuity is what's known as the reparameterization trick, which we are going to cover when we learn how this network is training, okay? But before that, let me break down the underlying concepts again and explain things clearly. So The two properties, I say they are continuity and completeness. Let's start with continuity. So continuity is like mainly if two input examples are similar, their latent representation should also lie like close together. In other words, I mean, closeness in latent space should correspond to closeness in data space. For example, I have two different images of the number 2, okay? Suppose that we have two different original images of number 2, okay? And what will happen? The images should map to nearby points. Otherwise, if there is any small movements in the latent space, this is going to produce kind of unpredictable changes in the output. Okay, so this is the idea of continuity. Now let's move to the second one, which is completeness. Okay, there should be mainly no empty holes here. Like for example, we can see these regions are disconnected. Okay, so we must not see that. So in the latent space, like we must not see that kind of empty space. Okay, so if we sample from any point I am going to randomly select in the latent space, I am supposed, or I would say we should still obtain a meaningful reconstruction. Okay, so it's not like I am going to check some random like point and it's going to give me like before kind of random looking output or noisy or garbage. Okay, image. So if we are going to sample, we are going to like have the new representation, and we are going to like make it go through the decoder. The output must be something that makes sense. Okay, and because the idea of generating, we are not generating, we are taking generative AI class, so we are not generating garbage. We are generating things that make sense. Okay, and here is the importance, sorry, again, of the term I already introduced, which is the regularization. So without regularization, these two conditions break down. So the latent encoding remains scattered and irregular. So this is exactly the problem that VAEs they solve. And the idea here is to have kind of a smooth, continuous, and complete space. Okay, and in this case, it makes interpolation meaningful and stable. Now, let me just note something, that this space is also, we are going to consider that it's like defined as a region and it is like limited, let me say, okay? Otherwise, there will be some empty like space. So we are going to consider it as a limited, well-defined region, okay? Let's now summarize. Okay, so we explained that in autoencoder, the latent space is unstructured with scattered or irregular representations. Okay, we also discussed how VAEs address this by enforcing a continuous and smooth latent space, making it possible to interpolate and generate gradual transformation between samples. So before diving into the details of training VAEs, and also another important trick, which is the reparameterization trick, I would like to show you a final result or final output so everything becomes clear before we move forward. Okay? See this. So in a VAE, what we do, we first define a continuous latent region from which all meaningful vectors should come. What will happen during the training is that the VAE is going to organize this region into different clusters. I would say you can consider a cluster like a pool, okay? Into different pools. And each of them correspond to a different class, okay? Let's say now we have the data set of MNIST data set. We have digits, 10 digits from 0 to 9. Mainly, we are going to have regions representing 0, some like regions representing 7, some other regions representing 9, and so on. So you can focus here with this cursor while it's moving. So we are within the same like region 9 here, for example. Here it's becoming 7, and if we are moving within the same region, it is giving the same number, okay? Here, all 1, for example, and so on. So the idea is that at the testing time, what will happen? Generating an image, as you can see here, becomes very simple, okay? We just sample a vector from this known region, and we pass it just through the decoder, because the region in this case is continuous, and small changes to the vector produce smooth transitions between digits, and this is going to create kind of gradual transformations, okay? So this is the core institution behind variational autoencoders that guarantee both, like we have the completeness and continuity. So this you are going to have at Lab 2, variational autoencoders, and I'm keeping for you the link for Lab 2. You just can go through Lab 2. And mainly this is the idea. So in this link of Lab 2, what you will find, this lab is implementing variational autoencoders in Keras, and we have almost the same structure like the previous lab. The only thing that now we are implementing variational autoencoder. Okay, so the theoretical things you are understanding in this video, when you are going through the lab, you are going to see them implemented, okay? And in this lab, is going to help you display a grid of sampled digits, like the one you can see here. And so you are going also to display the latent space cluster for different digits class, okay? Now, if you are reaching until here and you are understanding things perfectly, I would say you're already doing a great job. And I understand you might need to take samples. So this is why I am putting these results in the middle. You are understanding, you're taking a breath, and now you are ready to dive into more details, okay? Here we go. Just to summarize what we have when we are training any neural network, what we do the forward pass and then the backward pass. Now, we are going to summarize the forward pass. So, and what you see so far actually was only for the forward pass. Now, we didn't even cover exactly how the training process happens, the loss function, the backward propagation, all these interesting things we are going to cover now, okay? So, in the forward pass, essentially what happens? The encoder transforms the input into the parameters of a Gaussian distribution, which means its mean, mu, and variance, sigma. So instead of representing an image as a single point in the latent space, we will now represent it as a distribution. Now we understand words like space, distribution, like representation, latent space. Now we are becoming very familiar and comfortable with these concepts. If still fuzzy, just try to come back to the previous video. I also, videos, all of them, I also explain things in details. So from this distribution now, what we will do, we randomly sample latent points, and now we are going through the training process, and we are sampling, let's say, random point. In this case, maybe we can consider Z again, or we can like think of any like point, okay? What will happen now? If we are getting this like point, we are going to feed it to the decoder, and the decoder is going to map that back to the image space. So this setup allows to compute the different components of the, I would say, objective we will train the model with. And then we are going to backpropagate, right? We are going to backpropagate the resulting error through the network. By the way, more details about that are going to be discussed, okay? But now just let me describe things briefly. So please note, as I mentioned again and again and again, results we've seen so far come after training the network. So we haven't yet covered how to train a variational autoencoders, okay? How to do that? Let's zoom on the training details now, okay? If we do that, now training details involves the whole forward path, right? And also we're going to focus or zoom on the reparameterization trick in particular in this context. So in a standard autoencoders, like we said, we have a single vector z. This single vector represented by, I would say, single point in the latent space is like converted into a Gaussian distribution in the latent space in the case of VAEs. And again, it has mu and it has sigma. Instead of a fixed point, each input is representing a distribution. So all this is clear for us until now. And if we are going to sample, we are going to compute like components, and we are going to propagate them. We are going to compute some loss and so on. This is the main idea. And this is how the normal distribution looks like, right? So we sample like from this distribution, let's say we are going to sample a given point. And this point mainly like is going to go through the encoder, and then we are going to see what kind of reconstruction it has, okay? Now, what about the back propagation? So when it comes to back propagation, there is a problem, okay? And here, mainly the problem is within the sampling layer that we were discussing all the time, and this Gaussian and this story that I'm repeating again and again and again. There is a problem over there. The question is, do you even think that we can propagate through the sampling operation? You can pause the video and you can seriously think of it. Well, so the thing is, no, we can't. So this is where the reparameterization trick comes in, okay? So instead of sampling directly from the Gaussian distribution, we introduce random variable, often called epsilon, and this random variable, epsilon, is mainly introduced in order to handle the randomness outside of the network. Okay, this trick is actually super powerful, even that it's very simple. Okay, how it works? First, we sample a random point from a standard normal distribution, like you can see here. This is our variable epsilon. Then we scale epsilon by the variance of our approximated posterior distribution. After that, we shift it by its mean. It's just as we sampled directly from the posterior distribution. Expect that by using the reparameterization trick here, the process becomes differentiable with respect to the mean and variance, okay? So it's effectively the same as sampling directly from posterior distribution, but the reparameterization trick makes the whole process differentiable with respect to the mean and variance, as I mentioned, okay? So this reparameterization trick allows us to backpropagate perfectly. And what we do now, we are backpropagating through the entire network, okay? And this enables us to train the variational autoencoder end-to-end using standard gradient-based optimization techniques like ADAM, for example, okay? So now the encoder, sorry, I think there's this one. I will delete this from the slides, okay? So this is mainly the loss function of the autoencoder, but we are discussing the variational autoencoder. So in a variational autoencoder, the encoder and decoder each have their own set of weights. And so we have here like phi and theta. Even that, we have separate weights, not like the typical neural networks. We have two different sets of weights, but still the entire model can be trained end to end using a single loss function. Okay, we will use this one, by the way, but I will tell you how. So the loss function now depends on the input data, also on both sets of weights, phi and theta. Okay, and if we are going to look more closely at this loss, it has two parts. The first part is the reconstruction loss, which is just like the standard autoencoder. Okay, I was bringing the formula from the others, the slides from other video. I forgot them there. And the second now, so what this reconstruction loss from last time does? Okay, so it mainly measures the difference between the input and the reconstructed version, I would say the reconstructed input. Okay, and we want this error to be as small as possible, exactly like we did last time, and making it minimizing it, it makes it possible to achieve a faithful reconstruction. Okay, when it's equal to 0 means we are having the same original input as a reconstructed input. Okay, we want to minimize it. And now the second part, which is the regularization term we are covering today, which is the new thing for today's lecture. So this new component is the regularization term. Kind of it's going to, I would say, examine in more it's mainly designed to handle these kind of new distribution we are using, the Gaussian distribution. Okay, and now just we are going to cover this in more details. Fine. So the reconstruction loss is the same idea we saw before. It measures how different the reconstructed input is from the original input. Fine. And our goal is again to make this error as small as possible to achieve a faithful reconstruction. Now, the next part, which is now we are going to focus into the details of the regularization term. And here things really get more interesting. Remember that the encoder is learning a probability distribution over the latent variables given the input x. So the regularization term helps shape that distribution into a meaningful way. Okay, you'll see how. So when we regularize this probability distribution, what we are really doing is encoding, if we are, I'm sure, going through the encoder and decoder, and we are regularizing the probability distribution, we are following, I would say, a reasonable prior, okay, which is our initial guess about how or what the latent variable should look like. Okay, to do that, mainly how we need a way to measure how different two distributions are. Okay, and anytime you want to compare two distribution, there is already state of the art, and we already have some background. Okay, so if we want to see if two distributions are similar or different, we use something already existing and called the KL divergence. Okay, if you don't know, it's not a problem. It's like a way that gives you or return a numerical measure of the difference between two given distribution. And as we are using Gaussian distribution and we are measuring the difference between them, we are just going to use this, I would say, like a tool. Okay, so in variational autoencoders, the KL diversion regularization forces the latent space to follow a continuous smooth distribution. Okay, and this makes the interpolation meaningful. Moving, I would say, between two latent points is like creating, in this case, kind of gradual and realistic transformations like we just seen so far. It's like morphing one digit into another, okay? So this is thanks to the KL diversion. Now, the loss overall is computed using this formula, and this formula is mainly the sum of the reconstructed loss and the regularization term, okay? So mainly that's it. Just thank you so much. Now, at the end of the video, I'm preparing for you this table. It's like a recap. You can just pause, take a screenshot, and I would say this summarize everything for you. Okay? On the right side, mainly, you have the autoencoders limitations, and these limitations, like the deterministic encoding, like the unstructured latent space, scattered or irregular representation, the way that data could be reconstructed, not generated, like these autoencoders, mainly they do not model uncertainty and may overfit or memorize training data. All these limitations are covered or solved, I would say, with variational autoencoders. So for each of them, you're going to find what variational autoencoders did. Like for instead of having deterministic encoding, in VAEs, we have probabilistic encoding, where each input maps the distribution. We use or we introduce the mu and variance that allows the sampling and variability. The latent space is continuous and smooth. This is what we were explaining so far. This idea of introducing all these like Bayesian like foundations help us to reconstruct, that's okay, but also generate new and realistic samples, something that autoencoders don't allow generation, and even there is generation, it is fuzzy and it's garbage, it's not clear like we've seen so far. And in variational autoencoders we can model uncertainty, and we do use kind of it's regularized and generalizable. Okay, so thank you so much, and I wish you enjoy today's video. Thank you.